We can predict eclipses down to the second and land probes on comets. Yet one bad day of weather can still knock out an entire city. Today we're breaking down the world's most powerful natural disasters, explained earthquakes, volcanoes, hurricanes, heat waves, avalanches, tornadoes, floods, tsunamis, droughts, landslides, hailstorms, wildfires, and more. Here's the promise: I'll keep the core facts clear and simple. What they are, where they happen, why, then add the fresh science, how researchers at places like USGS NOAA and NASA actually study these monsters, and what their newest models suggest about risk, early warning, and climate links. By the end, you'll not only know what happened in history's worst events, you'll also get why they're so hard to predict and how to read the early signals that save lives. Quick reality check: natural doesn't always mean unavoidable. Human choices can amplify or reduce damage, from where we build homes to how we manage forests and coastlines. Think of Earth as a vast, slow-breathing system. Plate tectonics are its bones, oceans, its bloodstream atmosphere, its lungs. Disasters happen when those systems exchange energy too fast for our infrastructure to cope. To keep things friendly and practical, I'll use analogies. An earthquake is like a suddenly released spring you've been winding for centuries. A hurricane is a heat engine that runs on warm ocean fuel. A tsunami is the ocean's version of slamming on the brakes. Speed turns into height. A wildfire is what happens when fuel plus heat plus oxygen plus wind line up like 4 tumblers in a lock. We'll also spotlight famous events: Chile, 1960, Tambora, 1815, Katrina, 2005, the 2004 Indian Ocean tsunami, Europe's 2003 heatwave, not as trivia, but as playbooks. Each one changed how scientists model risk and how cities plan for the next hit. Ready to meet the biggest mover of them all? The hazard that can trigger several others like falling dominoes. Let's start with earthquakes. You'd think by now we'd know how to stop the ground from shaking, but nope. Every earthquake is like Earth's reminder that it's still very much alive. Most quakes happen when tectonic plates, the giant slabs of crust that fit together like puzzle pieces, grind, collide, or pull apart. The edges of these plates are like high-tension fault lines, storing energy for centuries until snap. That's the earthquake, a sudden release of built-up stress radiating through the crust like ripples in a pond. About 90% of all earthquakes, including the biggest, occur in the Ring of Fire, a vast horseshoe-shaped belt encircling the Pacific Ocean. It touches countries like Japan, Indonesia, Chile, and New Zealand, making it the most seismically active region on Earth. The most powerful quake ever recorded, the Great Chilean Earthquake of 1960, which reached a magnitude of 9.5. It lasted 10 minutes and was so strong, it changed the length of Earth's day by a fraction of a second. Scientists later confirmed that it wasn't just the shaking. It triggered a massive tsunami that raced across the Pacific, hitting Japan and the Philippines hours later. But power doesn't always equal tragedy. The deadliest quake remains the 1556 Shanxi earthquake in China, which killed around 830,000 people, not because of its magnitude, but because homes were carved into soft clay cliffs that collapsed instantly. It's a stark reminder that human vulnerability matters as much as geological force. There are different flavors of quakes too. Megathrust earthquakes, where one plate dives beneath another, are responsible for all of the top 10 largest quakes ever recorded. They're the reason we get those devastating double disasters earthquakes followed by tsunamis. In recent decades, scientists have made progress using satellite-based GPS systems and machine learning models to monitor fault movement in real time. They can't predict when the next quake will hit, but they can model where the stress is building. And here's a fascinating detail. Researchers at Caltech recently discovered faint electrical signals and changes in groundwater chemistry that might precede some large quakes, like Earth whispering before it screams. You've seen them in movies, glowing rivers of lava smoke pillars blotting out the sky, but volcanoes are far more than fiery mountains. They're Earth's pressure valves releasing internal heat and gases built up beneath the crust. A volcano is essentially a crack in the planet's skin, a vent that lets magma, molten rock ash, and gases escape from a magma chamber deep below. Most volcanoes line up neatly along tectonic plate boundaries, especially around the Ring of Fire, where 2/3 of all active volcanoes lie many underwater. That's right, the majority of volcanoes on Earth are hidden beneath the ocean. Every day, thousands of small underwater eruptions quietly build new seafloor-shaping continents in slow motion. But when one of these giants on land blows, the results can change history. The 1815 eruption of Mount Tambora in Indonesia remains the deadliest volcanic eruption ever recorded, with as many as 250,000 deaths. It blasted so much ash and sulfur into the atmosphere that it dimmed sunlight across the globe. The next year, 1816, was remembered as the year without a summer. Crops failed in Europe and North America, livestock died, and famine spread, all because one mountain sneezed. Then there are the truly terrifying ones, supervolcanoes. These monsters, like the Yellowstone caldera in the US, don't just explode upward, they collapse inward, releasing thousands of cubic kilometers of ash and gas. Fortunately, these eruptions are extremely rare. Only 4 have happened in the past million years. If Yellowstone ever erupted again, the ash fallout could blanket entire US states, disrupt air travel worldwide, and plunge Earth into a volcanic winter. Volcanoes are both destroyers and creators. The same magma that wipes out forests also forms new land like Hawaii, which rose entirely from repeated eruptions. Even Mars and Venus have massive volcanoes, suggesting that volcanic activity might be one of the universal signatures of a living planet. Modern volcanologists now use satellites and infrared sensors to detect changes in ground temperature, gas emissions, and subtle bulging that hint at pressure building below. These tools have saved thousands of lives, giving people hours or even days to evacuate before an eruption. And when those eruptions meet rain, ice, or gravity, another danger is born: landslides. Let's look at how entire mountainsides can suddenly decide to move. You might think mountains are symbols of stability, solid, unshakable. But under the right conditions, they can move faster than a car. A landslide is exactly what it sounds like: a sudden and powerful movement of rock, soil, and debris down a slope. It can happen almost anywhere, but it's especially likely in regions with steep terrain, loose ground, or heavy rainfall. And often it's not just gravity, it's a chain reaction triggered by something else: an earthquake, volcanic eruption, or even human activity like deforestation or mining. When an earthquake strikes near mountains, it can loosen entire hillsides. In 1920, in Gansu, China, one of the world's deadliest landslides occurred, set off by an earthquake that triggered 675 separate slides, killing around 200,000 people. That's not just falling rocks, that's whole valleys collapsing. In modern times, satellites help scientists detect slow-motion landslides, areas of Earth that move just a few centimeters per year. It's like a slow, silent warning. With the help of INSAR radar imaging used by NASA and ESA, geologists can spot ground deformation before it turns catastrophic. There's also a fascinating link between landslides and water. When a massive slide hits a lake or ocean, it can displace so much water that it generates a tsunami, or in extreme cases, a megatsunami. One of these hit Alaska's Lituya Bay in 1958, when a huge landslide sent waves more than 1,700 feet high, carving trees off entire hillsides. That's taller than the Empire State Building. But not all landslides are natural. In places where forests have been stripped bare, the soil loses its roots literally, and the first heavy rain can send it tumbling down. In Nepal, the Himalayas, and parts of South America, satellite data shows that deforestation multiplies landslide risk by up to tenfold. So when Earth shakes, slides, and crashes down, sometimes the result doesn't end on land. It moves into the sea, giving birth to something far larger and more destructive. Next, we're diving into one of nature's most elegant yet devastating phenomena: tsunamis. At first, the sea looks calm, the horizon still, the tide low. Then suddenly the water pulls away from the shore, exposing rocks and coral that haven't seen daylight in centuries. Curious onlookers step forward to take photos. Minutes later, a wall of water the height of a building races toward them at jet speed. That's the drawback effect, the eerie warning sign of a tsunami, one of nature's most devastating chain reactions. Unlike ordinary waves, which are stirred by wind or tides, tsunamis are born from massive displacements of water, usually triggered by earthquakes, underwater landslides, or volcanic eruptions. When the seafloor suddenly shifts, it shoves the entire column of ocean above it, launching a series of waves that can cross oceans undetected. In the deep ocean, a tsunami wave might be barely a few feet tall, but travel at over 500 miles per hour, as fast as a commercial jet. When it reaches shallow coastal waters, its speed slows and its height skyrockets. The result, a moving mountain of water. The 2004 Indian Ocean tsunami remains one of the most tragic natural disasters in human history. Triggered by a 9.1 magnitude earthquake off Sumatra, it killed at least 230,000 people across 14 countries. Entire coastlines in Indonesia, Sri Lanka, and Thailand were erased in minutes. But out of that tragedy came progress: the creation of a global tsunami warning system that uses deep ocean sensors to detect sea level changes and alert coastal regions within minutes. Even centuries ago, people understood the danger. In Japan, villagers carved warnings into ancient tsunami stones, marking the highest points the waves had ever reached and urging future generations never to build homes below those lines. Many who ignored them later paid the price. Today, scientists are learning how satellite altimeters can detect subtle sea surface bulges, potentially offering even faster warnings. Meanwhile, researchers at NOAA simulate virtual tsunamis on supercomputers to model where waves will travel and how they'll amplify. But tsunamis aren't the only way water can wreak havoc. Sometimes it doesn't come crashing down, it rises slowly and never leaves. Next, let's explore floods, the creeping disasters that reshape civilizations. It doesn't roar like a tsunami or explode like a volcano. A flood is quieter, but just as deadly. It's water out of place creeping over land that can no longer hold it back. Floods are among the most frequent natural disasters on Earth, and ironically, they often strike where humans most want to live, near rivers, coasts, and fertile plains. For thousands of years, civilizations have depended on rivers for trade, soil, and life itself. The problem: rivers have moods. Floods happen when water rises faster than it can drain away from heavy rain, melting snowstorm surges, or even failed dams. Climate change adds fuel to the chaos. Warmer air holds more moisture, making storms dump more rain, while rising sea levels worsen coastal flooding. One of the deadliest floods ever recorded struck China in 1931, when months of torrential rain caused the Yangtze, Huai, and Yellow rivers to overflow. The result: a tragedy that killed an estimated 2 to 4 million people, not only from drowning, but also from famine and cholera outbreaks that followed. In many ways, it wasn't just the flood that killed it, it was the weeks after. And that's something modern experts emphasize: floods often leave behind contaminated water, mold, and disease long after the headlines fade. Outbreaks of hepatitis A and E, respiratory illnesses, and even mental health crises spike after flood events. NASA's satellite network now tracks rainfall and river flow in real time, while AI flood models can predict when and where flooding is most likely. Cities like Venice and Rotterdam have built movable seawalls, while others like New Orleans have re-engineered wetlands to absorb overflow, nature's version of a sponge. But floods aren't the only disasters linked to climate and water. Sometimes when the sky itself turns violent, nature freezes its fury into stone. Next up, how hailstorms form and why the biggest hailstones fall where you least expect them. Imagine being caught in a storm that hurls chunks of ice the size of baseballs, or even grapefruits, straight from the clouds. That's hail, one of nature's strangest and most destructive tempers. Hailstones begin as ordinary raindrops inside a thunderstorm. But when powerful updrafts, columns of rising wind, lift those drops high into the freezing layers of the atmosphere, the drops turn into tiny ice pellets. Each time they're tossed back up, another layer of ice freezes around them like the rings of a tree. Eventually, they become so heavy that gravity wins and they fall. If you cut a hailstone in half, you'll see its layered history, much like the growth rings of an onion, proof of how many times it's been tossed around by the storm. Hail is most common in regions where warm, humid air collides with cold upper air. Especially Hail Alley in the United States, stretching through Colorado, Nebraska, and Wyoming. But some of the worst hail disasters happened far from there, in Germany and Australia, where storms have caused over $2 billion in damage each. Modern meteorologists track hail using dual polarization radar, which can distinguish between raindrops and ice, giving earlier warnings. NASA even uses weather satellites to map hail hotspots globally, helping insurers and farmers prepare. Fun fact: the largest hailstone ever officially recorded fell in South Dakota in 2010. It weighed nearly 2 pounds and was almost 8 inches wide. Imagine that hitting your roof. And while hail can shred crops, smash cars, and even kill livestock, it's also a reminder of how violently the atmosphere mixes. The same storm that makes hail can also spawn the most unpredictable and terrifying event of all: tornadoes. Let's head into the vortex. There's a special kind of silence before a tornado forms: a tense electric stillness. The wind stops, the air thickens, and then out of the clouds, a funnel begins to twist, stretching toward the ground like nature's own drill bit. Tornadoes are rotating columns of air that extend from a thunderstorm to the Earth's surface. Most of them are short-lived, about a few minutes and a few hundred feet wide, but the strongest can last for hours and tear through entire towns. They're born inside supercells, massive rotating thunderstorms. When warm, moist air near the ground meets cold, dry air above it, creates instability. Add a shifting wind direction called wind shear, and you get a horizontal spin in the atmosphere. Rising air tilts that rotation vertically, and the tornado begins to form. The United States experiences more tornadoes than any other country, around 1-200 per year. especially in Tornado Alley, a stretch of flat land across Texas, Oklahoma, Kansas, and Missouri. But they can happen anywhere, even in Europe and Australia. Tornadoes are rated on the enhanced Fujita scale from EF0 to EF5. An EF0 might just snap tree branches, while an EF5 can rip entire houses off their foundations and fling cars like toys. One of the deadliest tornadoes in US history struck in 1925, known as the Tri-State Tornado. It traveled 219 miles through Missouri, Illinois, and Indiana, killing at least 751 people. That record-breaking path still stands. Modern radar and storm-chasing teams have helped reduce tornado deaths dramatically. Doppler radar can now detect rotation inside storms sometimes 20 minutes before a tornado touches down. Meanwhile, NASA uses satellites to analyze cloud patterns that might hint at tornadic formation days in advance. And yet, despite all our technology, tornadoes remain deeply unpredictable. They're nature's roulette wheel, appearing without warning, vanishing just as fast. Next, let's face the heat. There's no explosion, no sudden roar, just relentless heat that won't let go. A heat wave is one of nature's slowest but deadliest killers. It doesn't destroy buildings like an earthquake or a hurricane. It exhausts, dehydrates, and suffocates quietly. A heat wave happens when a high-pressure system parks itself over a region, trapping hot air near the surface. Like a lid on a pot, it prevents heat from escaping and keeps recycling warm air day after day. The ground dries out, humidity spikes, and the air becomes heavier with every sunrise. Scientists define heat waves as prolonged periods of abnormally high temperatures, typically lasting several days or even weeks. And while we tend to associate them with deserts, they're hitting cities harder than ever before. Concrete, asphalt, and glass absorb and radiate heat, creating what's known as the urban heat island effect, making some city centers up to 10 degrees C hotter than nearby rural areas. One of the deadliest heat waves in recorded history struck Europe in 2003, killing over 70,000 people. Hospitals overflowed, power grids collapsed, and rivers dried up. Crops failed across France and Italy, causing food shortages that rippled through the economy. In a warming world, heat waves are becoming more frequent, longer, and more intense. A recent study in Nature Climate Change found that events once considered once in a century are now happening every decade. But heat waves aren't just about discomfort, they're also a fire starter. When soil moisture evaporates and vegetation dries, the stage is set for wildfires. Sparks from a power line or a lightning strike can ignite infernos that spread for miles. So, as we move from heat to flame, let's explore how fire, both destroyer and renewer, reshapes the very ecosystems that give us life. Fire, it's both the creator and the destroyer. For millions of years, nature has used it to cleanse, renew, and reshape the land. But in recent decades, wildfires have grown into something far more terrifying, faster, hotter, and almost unstoppable. A wildfire is any uncontrolled fire that burns forests, grasslands, or brush. It begins small, a lightning strike, a campfire spark, or a stray cigarette, but under the right conditions, it explodes into an inferno. Strong winds, dry air, and flammable vegetation combine into what scientists call the fire triangle: heat, fuel, and oxygen. Some ecosystems actually depend on wildfires. Forests in California and Australia evolved with trees like eucalyptus and sequoia that release seeds only through intense heat. After a blaze, new growth quickly follows, restoring nutrients to the soil. Controlled or prescribed burns mimic this process, reducing dangerous fuel buildup before a real wildfire can ignite. But when climate change meets human activity, balance turns to chaos. Longer droughts and record temperatures now make fire seasons nearly year-round. In 2020 alone, wildfires in California burned over 4 million acres, an area larger than Connecticut. Siberia, Greece, and Canada have seen similar devastation. There are 4 main types of wildfire behavior. Ground fires burn beneath the surface, feeding on roots and buried organic matter. Surface or crawling fires consume grass and shrubs. Ladder fires climb small trees and vines to reach the canopy. Crown fires burn treetops, the most destructive of all, capable of creating their own weather through pyrocumulonimbus clouds that can spark lightning and new fires. One of history's worst wildfires was the Peshtigo Fire of 1871 in Wisconsin, which killed between 1,500 and 2,500 people, the same night as the Great Chicago Fire, though far deadlier. Today, satellite imagery from NASA helps track fire spread in real time, while AI models predict which areas are most at risk. Yet even with cutting-edge tools, nature always has the final move. And sometimes that move comes not in flame, but in waves taller than skyscrapers. Next up, the ocean's deadliest breath: tsunamis. Imagine standing on a sunny beach, the waves retreat suddenly, the ocean pulling back far beyond the shore. The seabed is exposed to fish flopping helplessly on the sand. It feels strange, mesmerizing, and deadly. That sudden drawback is one of nature's last warnings before a tsunami hits. Unlike regular waves created by wind, a tsunami is born from massive displacement of water, usually triggered by an underwater earthquake, volcanic eruption, or landslide. When the seafloor shifts, it pushes or pulls a column of water across the ocean. The result, a wall of energy moving up to 500 miles per hour as fast as a commercial jet. In the deep ocean, tsunamis can pass unnoticed, only a few inches high. But as they approach shallower coastal waters, they slow down and grow, vertically compressing into monstrous waves that can reach over 100 feet tall. The 2004 Indian Ocean tsunami remains one of the most catastrophic in modern history. Triggered by a magnitude 9.1 earthquake near Sumatra, it struck without warning, killing over 230,000 people across 14 countries. Entire coastlines vanished and entire communities were erased in minutes. Japan, a country deeply familiar with these forces, has left stone markers known as tsunami stones dating back centuries. They read warnings like, "Do not build below this point." These ancient monuments remind future generations the ocean always remembers. Modern detection systems now rely on deep-sea pressure sensors, seismic networks, and AI-based alert systems that give people precious minutes to escape. But even with technology, the raw power of a tsunami shows how fragile our species is when the Earth itself moves. Next, the quiet killer that arrives not with a roar, but with silence and thirst drought. If tsunamis show us the violence of too much water, droughts reveal the terror of having none. They don't crash or roar, they linger. Slowly, quietly, they squeeze the life out of entire regions. A drought is a prolonged period of unusually low rainfall that causes water shortages for drinking, farming, and ecosystems. Unlike other natural disasters, its danger builds invisibly through weeks, months, or even years of dry skies. Scientists classify droughts into several types: meteorological droughts, when rain simply stops falling; agricultural droughts, when crops wither because of dry soil; hydrological droughts, when rivers, lakes, and groundwater dry up; and the most dangerous of all, megadroughts, lasting decades or even centuries. The American Dust Bowl of the 1930s remains one of the most haunting examples. Caused by a mix of severe drought and reckless farming practices, it turned the Great Plains into a barren wasteland. Giant dust storms called black blizzards buried towns and forced hundreds of thousands of families to flee, one of the largest internal migrations in US history. But drought isn't just about cracked earth and dry rivers, it's about ripple effects. As water disappears, food prices skyrocket, ecosystems collapse, and wildfires multiply. Lakes shrink into dust bowls, and even power grids fail when hydroelectric dams lose their water supply. Climate scientists warn that global warming is already amplifying droughts worldwide. The Mediterranean, California, and parts of sub-Saharan Africa are now facing the worst dry conditions in recorded history. In fact, the UN predicts that by 2050, 1 in 4 people on Earth could be affected by recurring drought. Yet humanity has always adapted. From ancient Persian qanats, underground aqueducts that delivered cool water through the desert, to modern desalination plants turning seawater into drinking water. Innovation keeps us alive when nature turns against us. But no matter how advanced we become, one truth remains: we are utterly dependent on the sky's mercy. And now let's step back from earthquakes to droughts and reflect on what all of this says about our fragile home planet. From the trembling ground beneath our feet to the roaring waves that swallow coastlines, every natural disaster tells the same story. Earth is alive. It breathes, shifts, burns, and freezes, all according to laws far older and grander than us. We've seen how tectonic plates collide to form mountains and unleash earthquakes, how fiery magma rises from the planet's heart to create volcanoes, and how that same heat can trigger wildfires or droughts that change civilizations. We've watched storms spiral into hurricanes, oceans pull back before tsunamis, and skies unleash both hail and heat waves. Every event a reminder that nature doesn't obey us. But there's something else hidden in these disasters' balance. The same earthquake that destroys cities also builds new continents. The same wildfire that burns forests also renews them. Even floods and droughts follow rhythms that sustain life over millennia. Modern science, from NASA satellites to supercomputers at MIT, helps us predict and adapt. But the deeper lesson isn't about control. It's about humility. The Earth doesn't belong to us, we belong to it. Maybe that's why after every disaster people rebuild, not because we can conquer nature, but because we're part of it. Each earthquake, storm, and drought reminds us how fragile life is and how extraordinary it is that against all odds, it continues. So the next time the ground shakes or the sky darkens, remember you're standing on a planet that's still evolving, a world that's constantly rewriting its own story. Question for you. Which of these natural forces fascinates you the most? The fire beneath the Earth, the storms above it, or the endless motion of the oceans? And if you love exploring how our planet works and why it sometimes fights back, make sure to subscribe for more deep dive explainers every week. Because understanding the chaos is how we learn to survive it.